Hi, everybody. This is Paul Luce. Although I am super bummed I can't be there with you in person this year, I miss everybody's smiling faces. I am very appreciative of the opportunity to share this information with you today virtually and talk about the SPDK Accelerator Framework. Okay, so let's jump right in. So we're going to talk about what is SPDK, including a high-level architecture. And I realize that a lot of folks out there already know this stuff. We've been presenting SPDK talks, we meaning community members from all sorts of different companies at SDC for several years. There are also multiple recorded sessions of SPDK talks this year. But if you didn't get a chance to see those, you'll get a quick update on that today. And if not, it'll just be reinforcing things. Okay, and then I'm going to jump into a little history for you. The original copy engine, right? What was that? Why was it put in place? And then right after that, we're going to talk about the new requirements, right? What drove us to take the copy engine and expand it and morph it and turn into what we're calling the Accelerator Framework now. A couple of cool reasons for doing that. Then we're going to jump into the Accelerator Framework itself. We're going to talk about some of the features, kind of how it works, what it's all about, what you can do with it, how cool it is. And then finally, I'm going to cover a deep dive of one of the accelerator modules, which you're going to find out is a plug-in module for the Accelerator Framework to support a specific piece of hardware. We're going to take a closer look at the Intel Data Streaming Accelerator module. Talk to you about what that is all about. Okay, the SPDK overview. So in my mind, first and foremost, when I talk about SPDK, I like to talk about the people. I like to talk about the community. We have a very, very vibrant community, folks from all sorts of different companies all over the globe, all walks of life, just very active in moving this project forward. And when I say moving forward, I mean contributing code, participating in discussions, helping out in Slack, adding test code, writing blog posts, representing SPDK in conferences, you name it. Everybody kind of does everything. And it's really cool. Everybody comes in and puts on their SPDK hat, takes off their company hat, and really focuses on making this project even better all the time. So if you're not familiar with SPDK, I certainly encourage you to take a look at this URL down here at the bottom, spdk.io. It'll reinforce all this stuff, right? SPDK is not one thing. It's a set of libraries, it's drivers. We've got some sample applications, we've got tools, we've got test code, we've got lots of documentation. There's lots of things that you can look at. Looking over to the right, you can see the feature categories, everything from network protocols to drivers to virtualization. Use cases are just as diverse. We're going to talk about infrastructure offload. There's database plugins, infrastructure as a service, enterprise is still a popular use case for SPDK, and then all the different things that it's optimized for, right? We optimize for CPUs and chipsets, for network interface cards, you name it. There's a place that things are optimized for, and the Accelerator Framework is another example, and we're going to be getting into that here shortly. Okay, so here's our latest high-level architecture diagram. If you've been following SPDK for some time, you see this changes pretty constantly, with the biggest challenge being how do you pack all this stuff into one PowerPoint slide? As you can see, there's a lot of stuff here. I'm not going to cover a lot of this since this is about the Accelerator Framework, but I will highlight, there's the Accelerator Framework right there. And I've got a much simpler diagram coming up here that will help you see exactly how it plays with the rest of SPDK. But before we get to that, let's talk about the original copy engine, right? Blast from the past. Like I said, the architecture diagram has been growing over the years. Here's what it looked like in 2016. Not a whole lot of stuff on there. So here's the question. Can you spot the copy engine in this architecture diagram? I'll give you a hint. It's right there. It's not called the copy engine on this architecture diagram because it was very simple and it was really focused around one thing. It was focused around the DMA engine known as IOAT, the quick data driver, Crystal Beach. It's got a bunch of different names, but it's been the predominant DMA engine that's built into Intel CPUs for several years. And what I'm going to talk about later, the Data Streaming Accelerator, is the next generation of that copy engine. But back to this copy engine. This guy does a bunch of things. We really only implemented copy and fill in SPDK. Those were the two popular things. But the last thing that we wanted to do is just build them in and make people write their applications specifically to talk to IOAT. right? We knew it wasn't going to be around forever. We knew someday somebody was going to come up with more offload engines that we wanted to cover. So a really thin framework was put around it called the copy engine that provided a generic API for copy and a generic API for fill, and then made the decision, depending on whether you had an IoT driver enabled in your SPDK-based application, whether or not to send it to IOAT or whether to send it to software, right? And if it was software, it would be like, a memset or a memfill, nothing, spectacular. But that allowed the application to not change code, moving from, hardware offload engine to software, depending on whether it was available or not. Okay, so what else drove the Accelerator framework besides the first item here on the list, which is let's build upon that, right? That's been very successful. Obviously, you don't want to force people to write to a specific piece of hardware. You want to keep it generic and low overhead, and make it as flexible as possible, as flexible as a Cirque du Soleil performer. Next bullet down here is we knew DSA was coming, and we knew DSA had just a boatload of features. I've got just a few of them listed here. We're going to talk a lot more about DSA coming up, so I won't go into too much detail on that right now. But with DSA coming, we knew we needed more extensibility. We needed to be a little bit more robust, and we need to make it easier for other community members to come in and add new accelerator modules. And we'll talk about what a module is here shortly. Another one is the introduction of virtual block devices for crypto and compression. This actually happened a couple years ago. It happened right around the time that the Accelerator framework was sort of started getting off the ground with a giant patch that did a bunch of renaming of copy engine to Accelerator framework. When we implemented those, the concept of a large Accelerator framework wasn't really there yet. We were just kind of getting things off the ground. So what you'll find if you go look at the virtual block device code for crypto, within that module, which is in the block device layer, you'll see that in a picture on the next slide. We're actually hard coding API calls into DPDK. So that's where we get our crypto and our compression from, either the DPDK crypto dev API or the DPDK compressed dev API. And that's worked fine, right? But what happens if somebody wants to use a different offload engine that isn't supported by DPDK? Well, they'd have to go in and rewrite one of these block device modules, and that wouldn't be very fun, right? So the plan here is, and you'll see more about this coming up, we're going to strip all of that hard-coded DPDK API stuff that exists in those two modules and make those Accelerator framework modules and change these block device modules to call the Accelerator framework instead. So if it's not obvious, the super cool benefit there is now if I want to switch from QAT to Mellanox to IAA, which is a new accelerator engine coming up. I'll touch on that briefly in an upcoming slide. It's as easy as making some calls to the Accelerator framework or initializing things differently, but no code changes to the crypto module. It will no longer call DPDK directly. It will call an SPDK, do crypto, or SPDK do compression, right? Stuff like that. So that's another big reason for beefing this Accelerator framework up. And then last but certainly not least is the introduction of infrastructure processing units. It is very likely to cause new offloads. And by new offloads, I mean either new capabilities, new offload engines, new capabilities within the Accelerator framework. I'll probably touch on one of those here shortly that I don't have documented very well because it's like super, super bleeding edge. In fact, I'll bring it up in the call to action at the end because it would be great to get some more people involved in those design discussions. Okay, so here is the infrastructure processing unit slide. I don't have a lot of detail on this. You can look at one of the other talks from Jim Harris that's recorded. He talks a lot about IPUs and in detail about what they have. The whole reason for putting this in here is to help you get an understanding of how they're relevant for the Accelerator framework and why is it important for IPUs. So at a real high level, you can see in this picture, we've got all the way to the left-hand side, we've got your host CPU, right? This is your your Xeon or whatever it is. And then connected via PCIe, we've got an IPU. And this is not a Xeon. I mean, it can be, but this is typically a much lower horsepower processing unit. It's a system on a chip, for more of a classic term. It has an NVMe Express interface to PCIe, right? So to the host, this looks like an NVMe device. Why is that important? Because SPDK is the one that's making it look like an NVMe device. And then the IPU does all sorts of value-added things, a lot of offload things, right? So you can imagine there's a, this is, they're also called, a category. This is SmartNIC, right? So there's a lot of network stuff going on in here. SPDK, we suspect, will be the main storage component for both the control plane and the data plane in here. So besides providing the NVMe emulation back up to the host, we also will do the NVMe initiator out the back end, either over to the network to go to NVMe Fabric targets that are on completely different locations, or if you had local NVMe devices, they could be attached directly right there. So that's where SPDK plays into here. And the fact that IPU is typically going to be a lower horsepower unit just simply means some more of the menial tasks, it just makes more sense to offload them, so you can focus the IPU horsepower on actually processing IOs instead of, doing the mundane stuff like, copies or compression or crypto, that kind of stuff. Okay, so moving right along. Now let's look at the SPDK Accelerator Framework. Again, this is a dumbed down picture of the full architecture view that we saw earlier. It's really got the main relevant things that are applicable here to this talk. So you got your top end here with the target and the protocols, iSCSI, NVMe Fabrics, vhost, that kind of stuff. And then down in the storage services layer, here's the block device abstraction layer, right? So this is where a lot of companies will come in and add their secret sauce here with a virtual block device, basically allowing them to add some sort of data transformation capability as the operation moves down the stack. So the Accelerator Framework sits off to the side here, and it's usable by any component with SPDK. And today we have DSA support. Here's where I mentioned IAA, which stands for Intel Analytics Accelerator. It's a different accelerator with a slightly different focus than DSA, but it's available in there today. We've got IOAT that's available today, and then we have software-based stuff, which when it makes sense, we use ISAL. And hopefully you're all familiar with ISAL. If not, you can go check out ISAL out on GitHub. That's another Intel project out of some team members out of the team that a lot of us SPDK folks are on. And the reason we use ISAL in there is that there are some opportunities there to do more accelerated software capabilities than just a dumb memset or a memcopy, right? So a great example is compression's an example. CRC32 is an example that ISAL can do a better job than just standard calls. So we implement those in the software engine. And then QAT, which actually probably a better way to put that would be crypto dev or compress dev would be two modules that are work in progress right now. And then Mellanox is currently supported behind the DPDK interface as well. So that will be coming out as its own Accelerator Framework module. Okay, so let's jump into the Accelerator Framework here with a fairly high level picture. But let's start at the top. You can see we've got our application is going to send in these generic calls. They start with SPDK Excel, right? So you're going to submit a copy or a fill or a CRC32C. Those would go directly to the Accelerator Framework. And I'll map through those here in just a second. But moving down the stack or moving down the picture here, we also have accelerator specific calls or hardware offload specific calls. So in this case, we can call the DSA low-level public library, the DSA public low-level library, with a call called SPDK IDXD underscore something, right? So every capability that DSA offers, we offer at a finer level than the Accelerator Framework. I'll talk a little bit more of that in a minute. By the way, IDXD stands for Intel Data Accelerator Device Driver or something like that. It's what the kernel guys use. So if you look in the kernel and look at IDXD for drivers, that means the DSA driver. We call it DSA in a lot of our materials and a lot of our code, but provide the linkage to the kernel. We kept IDXD in a lot of the APIs, and IOAT and all the similar low-level libraries have very similar calls that are specific to that. So let's go back to the top here and say you submitted a copy. I submit a copy, and let's say I don't have a module installed or initialized that can handle copy through an offload engine. The Accelerator Framework will do that in software. So it'll send it to the software module and say, hey, you go fill this copy request and take care of it for me. Now let's say I have DSA installed. Okay, so now any of these calls that come in, if DSA has been charged with handling that opcode, the DSA module will take over, and the DSA module will do its stuff, and I'll talk about what its stuff means here in a minute. And then it will forward that request to the low-level library, the same exact APIs that the application can use directly if it likes, right? So we provide this flexibility for a reason. This is a little bit lower overhead path, but you do lose some capabilities, and I'll talk about what those capabilities are when we do a little bit deeper dive into the DSA module. And then finally, just for completeness, let's say that DSA couldn't field that command for whatever reason, and IOAT would be doing it. The Accelerator Framework would pass it to the IOAT module. The IOAT module would do what it does, basically converting it to an IOAT command. Again, there's some other stuff. We'll talk a little bit about that on the DSA side. And then it would pass it down to the low-level library, again, using the same exact APIs that the application called directly, if that was desirable for whatever the use case is. Okay, so that's kind of the big picture. Now let's talk about how these things are where the flexibility comes into play. The Cirque du Soleil flexibility comes into play. So within the Accelerator Framework, we have a pretty simple table, and this table maps opcodes to available modules. Okay, and these modules are these software backend plugin modules. Again, I'll talk about the roles and responsibilities coming up here in a minute. But initially, when the Accelerator Framework comes up, it's going to map each opcode to whatever available module has been initialized, and it's going to do so in the order in which they came up. So it may not be optimal for what the application desires, right? Maybe a bunch of stuff is going to the software module and you want it to go to the DSA module, or whatever, and you can slice and dice this however you want. So in this example, these first 6 opcodes all map to the DSA module, and compress and encrypt map to QAT and the Mellanox module, respectively, right? These are all extremely flexible, right? And we can map these however we want. This is just the initial static mapping in this particular example. Okay, so let's see exactly how we do that. Now, I put engine/module here for a reason. Right? Like any open source project, there's some historical baggage that comes along that we chip away at over time. I mentioned the word copy engine for a reason earlier. Initially, things were called engines. And then when we did the Accelerator Framework, we started calling them modules, but in some pieces of code or APIs, they're called engines. We're consolidating on the word module, but we're not quite there yet. So to avoid confusion, I'm just saying, if you see engine or module in the Accelerator Framework, they mean the same thing. It's the plugin thing that goes into the Accelerator Framework. Okay, so let's talk about discovery. So if I'm an application and I need to know, hey, what's out there, right? What do I have for modules and how are they mapped to opcodes? I can do it via a C API, which is get opcode engine name. So I can pass in an opcode and it will tell me what engine is responsible for that. Or I can do it with an RPC, right? So if I have somebody who's not recompiling the code or not writing the code, you can do this in RPC with Excel get engine info, right? And this is going to change to Excel get module info one of these days, but again, that's why I'm listing both here. So in this RPC example request, you can see the request comes in, hey, give me the engine info. Tell me everything you've got that's been initialized and what opcodes they potentially handle, right? So this doesn't show you the mapping. This just shows you what is available, right? This is your discovery operation. So in this response, you see we get this JSON formatted response where the first element is, hey, I've got an engine. It's the software engine. Here's all the opcodes that it can handle. Oh, I also have DSA that's available. It's initialized. You can use it. And here are the opcodes that it handles, right? So this gives you an idea of what you've got available. Now, let's say you want to go change what the assignments are or get an idea what the assignments are. Again, we can do this either through a C API or we can do this through an RPC. And it's as simple as assign opcode, right? So you're going to assign an opcode to an engine, and we do the same thing with an RPC. And here's an example. So the RPC is called assign Excel assign RPC, Excel assign opcode, and we're going to the Excel example request says, hey, I've got the opcode copy and I want to assign it to the software engine. So what the framework is going to do is going to go make sure that the software engine is available first and foremost. If it is, it's going to check and make sure that it supports the copy opcode. And if it does, you're going to get a response saying, hey, done deal. Copy commands are not going to be handled by the software module. I could have just as easily put the DSA module in here and it would do the same thing. It's going to make sure, number one, DSA is available, and number two, DSA supports copying, and it would give me a true. If either one of those were not the case, you would get back a false value, and you'd have to know, oh, okay, well, I can't do that on this platform for whatever reason. Either I didn't load I didn't initialize the modules, or the hardware just isn't present. Okay, so let's jump on to the DSA section of this. Hopefully all this is making good sense. Now, this is nothing to do with SPDK. This is just a DSA overview. I included this because this is a really cool piece of hardware. This has been a long time coming. Like I said, this is the next generation of IOAT, and they've done a tremendous amount with it, including adding opcodes. We're not going to get into all the details of how you submit and complete operations, but it's pretty slick. It's all designed for performance and low latency, and it's got some really cool features. So the key point here, that the reason I put this diagram in here, and by the way, the complete specification is public. It's available at this link down here. It's a pretty easy read. Tells you everything you'd ever want to know about DSA. But the key point here is that DSA was designed up front to be used either in kernel space or user space. Okay, so you can either have it completely contained within the kernel, and you can have other kernel modules make use of DSA in ways that make sense. And there's a whole laundry list of stuff that you can do with DSA in the kernel that are being worked by various engineers in the Intel community. Ben Walker's got a talk. He's doing some work with DSA in the kernel that has nothing to do with SPDK. It's just a cool piece of hardware. And then you can also expose work queues that were with continuing to maintain control of the DSA hardware by the driver. You can expose work queues to user space, right? With applications like SPDK in mind, or there's other potential use cases as well. So your user space application can say, hey, kernel driver, give me a work queue, and I want to be able to submit operations directly to DSA without going through the kernel driver. I want direct access to a work queue. So that was built in as part of how DSA was designed. So as a follow-on to that, right? What are we doing in SPDK? Well, we've got two modes that we can operate in. We have the default mode, in which case it's very much what everybody's used to if you're used to SPDK. We have a user space driver that is responsible for everything, right? So we unbind the kernel driver if it's bound to the hardware. We unbind it and bind it to either UIO or VFIO, depending on what your choice is, and then SPDK is responsible for initializing the DSA device, and configuring work queues, and doing all that stuff. The alternate mode. Oh, and by the way, you'd want to do that if that's what you're used to, right? If you have complete control of the hardware, or if you definitely do not want any kernel dependencies, right? You say, I don't want to have to use the latest greatest kernel, or I don't want to pull in a kernel module, and backport it to whatever my kernel is. Then you can use the SPDK user space driver and be kernel driver free. Now the alternate mode is where we don't unbind the kernel driver from the hardware. We actually let the kernel driver initialize the hardware. And then there's a couple different ways that we can configure work queues so that SPDK can submit to those work queues as if SPDK was the one that created them. And this is outside the scope of SPDK. There's a tool called Excel Config. You can also do this a couple different ways, and it's all documented out there about how you do it. But essentially, in this case, the kernel driver owns initializing the hardware, and you have to use some other tool to create work queues, and then you basically just fire up SPDK and tell it, hey, I'm using the kernel space driver, and SPDK from that point forward, it operates exactly the same way as if you were using the user space driver. In other words, the submission and completion of operations is the same identical code. There's no conditionals, there's no compilation, there's no nothing. It's the same exact code. The only difference between these two is who initialized the hardware and who created the work queues. But after that, it's identical. So this is an important point, right? A lot of folks that are used to SPDK are used to seeing this user space versus kernel space as a performance play, right? That, oh, well, you definitely want to use a user space driver for performance. That's not the case here, right? And that's why we outline a kernel mode driver. You'd want to use that if you want to share the hardware with other things, right? And it could be other kernel mode applications or other user space applications, right? So let's say you're in a Kubernetes environment, for example. If you just had the SPDK user space driver and you want to use it in Kubernetes, you'd have a challenge trying to use DSA amongst multiple containers. It would be tough if it's even doable. I mean, that's why we did the shared mode thing, right? So this would be pretty easy. Now you go in and say, all right, I'm gonna have my container request a work queue. Somebody else, the kernel driver, owns the hardware, and multiple containers can request work queues in that scenario. And then SPDK can be running in each one of those containers and talk to those work queues and not worry about owning the hardware that should be owned by a more centralized resource. So there's really no measurable performance difference that we found. There's probably something someone could do somewhere that would see something weird, but essentially this is not for performance reasons. You would choose one or the other based on what your use case is. Okay, so let's talk a little more about the roles and responsibilities of the framework and the module and the low-level library. A lot of it's probably clear already, but it's good to summarize and repeat some of this stuff. And there's a few little new tidbits of information in here as well. So the Excel framework itself is primarily responsible for initializing modules, right? So it's going to go out and start up modules, and those modules in turn do their things. It also manages the opcode to module mapping, the stuff that we covered early, right? So it's the one that provides the capability of saying, I want these 3 opcodes to go to that module, and these 3 to go to that module, and this one to go to that one, right? So you can set those up and slice and dice them however you want. It also manages tasks, right, and the context within the tasks. And this is a fairly common construct within SPDK. The Excel framework has a pool of tasks, and each one of those tasks is associated with an operation that comes in, and those tasks track things like, who do I send the callback to? What are the callback arguments when this thing completes? All the stuff it needs to pass on to the low-level library. And then finally, it submits these tasks to the modules, right? So the DSA module then, using DSA as an example, has to manage flow control. So this is specific to DSA. Well, at least in this case, it is not, every piece of hardware that does offload can have a different way of submitting and completing IOs and have different requirements around flow control. Specific to DSA, you definitely want the software to know how many operations are outstanding, know what the limits are, and never push it. Because if you go over the limit, you're going to be in error handling space and crater performance. So flow control is the responsibility of software. We do that in the DSA module. So that's a good example of, let's say an application didn't want us doing the flow control. They've got a different way of doing it. Maybe they put a restriction somewhere else that doesn't require queuing of things. Then call the low library. Don't use the Excel framework, right? And then you've got the responsibility to make sure you don't overflow the device. Okay, and it of course converts Excel framework calls to DSA calls, which is not rocket science. They both basically have the same parameters, right? But one is abstracted so that you don't have to change code flipping back and forth between accelerators, and one's tied to the accelerator itself. And then of course it calls the DSA library. Here's another important one, that if you're writing to the low-level library, you'd have to do this yourself. It registers a poller, right? And that poller runs periodically and calls into the low-level library, basically saying, hey, do you have some completions that I can handle? If so, pass them on over. And then it looks them up in the task context to find out what the callback is and the callback argument, and it completes them accordingly. So again, if you were to write to the low-level library yourself, that's something you'd have to do. So that's another benefit of using the Excel framework beyond all the stuff we've talked about already. Okay, and then finally, we've got the low-level library itself. It discovers and initializes the hardware. There's some assistance there from DPDK when it comes to PCI stuff, but that's the DSA low-level library's responsibility. It handles address translation, so we don't have to worry about that in the Excel framework, right? Depending on what the requirements are of the underlying hardware, that may be different, so we do that in the DSA library. And then, of course, it actually does the submission to the hardware, and it reaps completions from the hardware. And then it does something called transparent batching, which I'll talk about on the last slide, which is kind of specific to DSA, but not really. The concept is fairly portable depending on what your hardware looks like. You'll see that here in just a second. And then, of course, finally, we go down to the hardware. Okay, so there's the basic roles and responsibilities of the framework, the module, and the library. All right, so let's talk about this thing called transparent batching, and what does that mean? Well, the goal of this feature is to make the most of the hardware. What we discovered after playing with DSA for a while is it is just lightning quick. You submit an operation and it's done before you're done submitting it almost. It's that fast, right? So what we found was that without some other means of keeping it busy, if we just periodically send it things, it's being completely underutilized, right? So we want to utilize the hardware as much as possible, right? So we came up with this scheme, and it was actually kind of borrowed from what we do in the NVMe driver. But for DSA actually has an opcode, a batch operation that allows the device driver to submit a series of operations in a single command, right? So what you do is you build up a chain of descriptors, of DSA descriptors, and they can be completely independent. They don't have to be related at all. You're just batching a bunch together for efficiency in the submission process. And then you just submit that batch one time. You give it the address at the start of the chain, and then the DSA hardware will DMA that whole chain down and just start going to work. And there's some really cool options that DSA has for how you want to handle each one of the, the child elements, if you want to call them that. But we're basically treating them as completely independent operations, and we're doing the batching to keep the hardware as busy as we can. So we originally at one point in time had this capability exposed to the Excel Framework API, and we might add it back again, right? And these things are pretty dynamic depending on who's been working on it, who's got different use cases and other different cool things we can do. But at one point in time, we did have the ability for an application to say, hey, start a batch of operations, and then it could, just start filling that batch up with as many operations as it wanted. And then when it was ready, it could say, hey, okay, now go send this batch down. And I'll talk about that more here on the next slide as to where we might see some version of that coming back in the future. But for now, we found the best way of using batching was this mechanism. And what this mechanism is we say, let's say an operation comes in to the Excel framework and it comes to the DSA library. The DSA library is then going to say, the low-level library, after it goes to the module, is going to say, okay, you've got a copy operation. I'm just going to hold on to it, right? I'm not going to submit it yet. I'm going to wait and see how much more work you've got for me to do over the upcoming period of time. And it will submit that as a batch of operations when one of two things happens. Either that batch is full, and I'm going to talk to you in a second about what that means, or when the poller runs, right? So as with anything, when it comes to submitting batches of things or, coalescing things, whatever term you want to use, it's a fairly common practice in these kind of IO operations. It's a trade-off, right? The more you batch things, the more efficient you get potentially in the submission, depending on the hardware and completion of these things. But you're adding latency, obviously, right? So we're adding some amount of latency. So we want to have that balance. So what we've decided in the low-level library right now is our batch size is 16. So here's an example of a batch. This batch will fill up when it hits 16. Right, and it's just a bunch of dissimilar commands, right? And if the poller runs before this batch is full, we're going to say, all right, we don't want to add any more latency to this than we need to. Just go ahead and do these 5, or do this 1, or do these 8, however many are ready. Now, if the application is using DSA heavily and really bombarding with operations, we'll find that this will fill up, and we'll submit multiple batches before the next poller runs. Right, and that's great too, right? That's where that trade-off is, right? So we never are going to pay more latency than the time for the poller to run, and we're never going to add so much latency that we're going to pile up 64 of these things before we submit them, right? So that's kind of what the magic number is now. This has given us some really good performance, and again, we're looking forward to having the Excel framework and this hardware out there in the community here soon. And get some more feedback on other optimizations that we can think about. Okay, so what can you guys do? Well, get involved. Like I said, this is a wide open, very vibrant community. We love having new people come in and bring in new ideas. We love diversity of thought. It really has made SPDK not only a super fun community to work in, but it's made the code base really strong and of really high quality. And I'm not just saying that because I'm one of the contributors. I'm saying that because that's the vibe I get from everybody that talks about SPDK. That it really is a shining example of how an open source community can be super successful. So get involved. The Accelerator Framework is not done. Like I said, there's a bunch of modules that are under construction, including the compression and crypto stuff. There's another thing that I mentioned I would talk about related to batching. And I don't have a slide on this because we are still right early in the design phases, but it's relevant for infrastructure processor offload, as well as some other use cases. But the idea is, let's say you've got multiple offload operations that you want to do on a particular data set, but you don't want to do it 2 or 3 times independently, right? So let's say you want to do, compression and crypto, right? If you were to do those independently, you are copying the data back and forth between your your offload engine 2 or 3 times, or let's say you want to do a copy and compress at the same time. We don't want to copy it to a data buffer and then have that data buffer copied to the compression engine and then have the output copied somewhere else, right? That's kind of what we have to do today, except in certain cases, like with DSA, where we have an opcode that does copy plus CRC32, right? So the idea is let's get the Excel framework smart enough so that you can envision an operation coming down the stack, and we want to do something kind of similar to what we talked about with batching, what I just talked about with batching, where you say, all right, I'm going to start this operation now, but I don't want you to actually do anything just yet. But I know I'm going to want to copy from this location to this location. And then somebody else down the stack is going to say, oh, and I'm going to want to do a CRC32. And somebody else may want to do something to it later. And at some point, you get down to the bottom of it and you're going to say, okay, now go do all this stuff. And it would be the Accelerator Framework or a side component of the Accelerator Framework's job to say, all right, what do I have hardware-wise that can do what the software wants me to do? It wants me to do a copy and a CRC32. Do I have anything that can do that efficiently? Oh, I do. I have DSA. I'll just send one opcode and do it, right? Or if it's stuff that it doesn't have hardware available that can do both in one operation, it'll do it kind of the slow way and just do them both together. But the idea is we get all that in place. And again, this design is not fleshed out yet at all. This is something that we'd love to get more feedback on. We'd love for the ability to have that framework in place so that the pipeline can add these operations as it goes down, and then at the end, do the best thing possible given the platform that I'm running on. So that's another really cool thing that you can get involved with. Okay, please don't forget to rate this session. Right, your feedback is always appreciated by not only by the SPDK folks and the SDC folks, but by us presenters as well. It's good to hear what you have to say. And with that, we'll wrap it up. Thank you all for listening. I appreciate it.